Additionally, he is a faculty member at Arizona State University. Dr. S is a certified GIS professional, a certified arborist, a Part 107 certified UAV pilot. As a geospatial evangelist, custom geospatial solutions provider, and geographic researcher, Dr. S is widely versed in all things geodetic and is a geoholic. Dr. Spivosky, with that, the floor is yours.
All right. Thank you so much, Matt. Hopefully everybody can hear me. If you can't, please throw it out in the chat. We checked audio levels, but you never know. Thank you for the introduction, and I appreciate everybody out there right now that took some time out of your very busy week to spend the next hour with URISA Texas and myself. I just also want to say thank you to all the different URISA Texas volunteers out there that make these types of events happen, the Mappy Hours. It's just an exceptional team. And if you've ever thought about volunteering, quick plug, I do recommend you all checking that out. So what are we going to be talking about today? Hopefully you signed up because you saw the title, and so you are at the right place. We're going to be talking about advanced field data collection methods and the future of GIS. Let's talk about a little bit of the agenda. So we'll have a quick introduction of who I am. Matt just gave me a great introduction, but we'll talk a little bit further about who I am and, what is this dude talking about? What's my background? Well, from there, we're going to segue into what I call the geospatial foundation, aka Geodesy. Oh yeah, so perhaps you haven't even thought about Geodesy at your job for quite some time, and it's probably like the last time you've ever even thought about the concept was maybe in a college class 5, 10, 20 years ago. So we're going to set a foundation, sort of a pun, because Geodesy is the foundation for the rest of the presentation. Well, I'm also going to review what I would call the current state of geodetic affairs. And what I mean by that is how are people today, and especially the GIS, but geospatial worlds, how are we interacting with, projections in geodesy and these advanced data collection technologies and methodologies? So we'll talk through that. Of course, we're going to talk a little bit of GNSS basics, so global navigation satellite systems. Hopefully you'll learn a little bit there as well. We'll segue into terrestrial remote sensing, so some of the more fun, novel, new technologies, things like LiDAR and drones and things of that nature. We'll also talk a little bit about Earth observation collection methods. So if you've not been buried under the sand or under a rock for the last few years, you probably realize there's a ton of really cool data out there, especially imagery and some other types of data sets that are all taken from satellites floating around in synchronous orbit around the Earth. And so we'll talk about that. And I am going to finish off the presentation about the future of GIS, what I think geographic information systems and geospatial, quote unquote, is up against in the near future. And I'd like to make a challenge and a call at the very end of the presentation for you all on how we kind of move forward. We are going to stick to a strict 1 hour. So at about 10 minutes out to 1 o'clock Central Time here in Texas, we'll go into a Q&A mode. And I'd encourage anybody who wants to ask a question at any point during the presentation, please go ahead and type the question in the chat and we'll get to it at the end. I also just want to make a quick point that a lot of the images in this presentation are not mine. I found them all throughout the internet, different companies and organizations. In the lower right-hand corner, there is a source. So I'm giving credit where credit is due. I'm not claiming that I made all of these images. These things will be made available afterwards. So if you'd like, just reach out to URISA Texas. Okay, without further ado, let's go ahead and jump in to the presentation. So who am I? It was already mentioned, but I like to call myself a geospatial evangelist. I'm sort of a dichotomous person in the world of geospatial. I am both a pseudo-academic, but also been in the private side, corporate world for the last 20 years. So undergraduate, University of Florida, actually in history and anthropology with a minor in education. So I got my geospatial start in mapping archaeological projects. I did a master's in GIS at Arizona State University, of which after that I started teaching, and it's been about almost 14 years of teaching since then. Following that, working full time, I was able to find a PhD program and went ahead and got through that. and actually studied behavioral geography. So in my private side world, I am the Geospatial Solutions Director for Bad Elf, a low-cost alternative GNSS. You will see some Bad Elf imagery throughout this presentation, but you're going to also see a ton of imagery from other providers like Trimble and Leica, et cetera. So my goal here is to be as agnostic as possible. Of course, I work for Bad Elf, so there's a little bit of a connection there. But my goal here is to show you that these technologies and practices exist, and it's up to you to do your due diligence and find the correct solution for you, whether it's something like Bad Elf or ASU. And you can see in my little window here, I'm wearing my Bad Elf shirt, but I'm also got my ASU Sun Devils background. So working from both perspectives. Should also mention that I've done a lot of research around LiDAR, augmented reality, GNSS, visual scenic resources, behavioral geography. So I've got a kind of a wide plethora of my background. And what I find is a lot of people in the GIS geospatial world also kind of have similar, very large backgrounds. If you are on LinkedIn, follow me. I'd love to connect with you. Part of my fun here with being an evangelist is I love to talk to all the people out there and just continually get feedback and continue to grow in this geospatial world, and we can support each other. So let's talk about geodesy. Oh yeah, so geodesy. What in the heck is geodesy? Wikipedia states that geodesy is the science of measuring and representing the geometry, gravity, and spatial orientation of the Earth. Perhaps you've seen these little images before. We've got a spheroid on the left, an ellipsoid in the middle, and what's called a geoidal model on the right. Many people realize that geodesy is kind of from that ancient Greco-Roman terms, right? Geo and deci, kind of looking out and navigating and studying the Earth and where you're going. We all kind of understand that, the shape and the size and the orientation. What most people forget is that geodesy, this foundation of all these things of GIS and geospatial, actually involves gravity, right? And so gravity, or the geoidal model, which you'll see in the right-hand corner right there, gravity plays a big factor in any type of data collection. And that's really important to understand, because think about this, all around the Earth, the sea levels are different. And so how you define, for an example, elevation or your height values or your Z values actually is directly influenced by the gravitational pull in that area. And so you see the geoidal model all kind of bumpy, and that's actually trying to represent where you have more gravity and less gravity. So as the water moves, that actual sea level changes. And so my point to make here is that if you haven't thought about geodesy, start thinking about it. Secondly, if you want to be accurate and precise, we have to understand these things. So on the left-hand side here, this was a student of mine about 6-7 years ago in an advanced GIS class, and I really liked it. This is her image on what she called Geodesy Drop. And so imagine you're taking a ball and you drop the ball, and the ball starts as the most basic kind of shape of the Earth. It is a spheroid, right? You're in 5th grade planetary sciences, and you've got, you know, your solar system diagram made or whatever for the science fair. You know that the Earth, we call it a circle, right? It's a spheroid. It's very circular. The fact is actually that the Earth is actually wider around the equator because of centrifugal forces. The Earth spins, and because of that, we actually are bowed out and actually a little thicker around the belt line than we are tall. And I'm not going to read all of this, but keep in mind that the most basic 5th grade definition of the Earth is circular, but we know that's not true. So then we start talking about what's called ellipsoidal height, or the ellipsoidal shape of the Earth. And this is more of a circle that's been sat on and squished out. It is also, in terms of horizontal components, it is what we call a grid system. And so it's an interpolated system. If you look on the image on the right-hand side, it's sort of hard to see, but see this dashed line where my mouse is going through? Notice that this is called the ellipsoidal line. Notice how that's all smooth and round? Well, nothing is really that smooth and round on Earth, right? And so the ellipsoid, in terms of elevational value, is a computated a number. It doesn't actually represent real space, and we're not going to get into that too much. But what I do want you to understand is that natively, when we're collecting, say, data with GPS, right? So you're going out collecting some field data, maybe with Esri Field Collector, or field maps rather, actually the satellites are projecting its elevation in geoid, in ellipsoidal value natively. So this is that kind of very interpolated surface. As we kind of go up, as the ball bounces up, we actually add in what's called the geoid. That's that gravity model I was talking about. And so what you can see here is you see the geoid is this bumpy thing having to do with gravity. The ellipsoid is this interpolated surface that most GIS just assumes at the gate. But the moment we start talking about advanced geospatial, we have to understand that there's more definitions here. So that the concept is when you look at like a planned data sheet, like of a town, an engineering project, something a surveyor would stamp or a registered engineer would stamp, they are almost always in what we call orthometric height. Orthometric height is literally the geoidal height plus or minus the ellipsoidal height. So to get to where, when you're saying you're driving up to Aspen to go skiing for the day, maybe, and it shows you the population on the sign, welcome to Aspen, population, then it says elevation. Usually that elevation is what we call mean sea level. Mean sea level is also referring to that geoid. So I just want to express one more time that depending on what you're doing, you need to understand the definitions of geodesy in terms of elevation. You've got ellipsoidal height, you've got this thing called the geoid, and at the end of the day, if you're thinking vertical values, you actually probably want to get to what's called orthometric height. I guarantee there are many people out into the crowd, and you can raise your hand if you want in the chat. But who out there does drones? And if you do drones or LiDAR, for an example, you're probably going to realize you've seen these terms right away, right? When you process your imagery data, you've got to tie it to some things, like you have to project it, right? And maybe you've noticed where elevational values are off, maybe by like 100 meters or so. This is usually a bust having to do with the ellipsoid versus the orthometric height that incorporates a geoid, right? And you can literally see here that the Earth's surface is not necessarily either of those. So pretty convoluted right out of the gate. So when I bring all this up, it's not to scare you, and we don't have time today for me to go into the depths of geodesy, but I do recommend YouTube University. Go on YouTube, check it out, type in geodesy. There's a bunch of really great things. But let's hit home. So who here, most of us probably use Esri or QGIS products. In the Esri world that I'm the most familiar with, how many times in either ArcMap or ArcPro you've gotten a box that says geographic coordinate systems warning, or transformation warning, or unknown coordinate system, or you've ever had any type of message from Esri pop out that says ding, 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 like, hey, wait a minute, there's something happening. You added a layer and it's going, hey, the base map layer and your new feature is on a different coordinate system. What do we want to do? And what do we all do? We hit close or accept immediately. We don't even read what's happening on the screen. And I know you are just like me, and you have done that 1,000 times. I'm going to challenge you to think through this a little bit. Not that you have to follow every dialog box when it's giving you a systems warning, but there is grave consequences downstream if we don't understand geodesy. So left, right, up, down, very simple, right? So we've all probably heard of WGS 84, NAD 83, local versus global, right? When also has to do with when they were made. There's actually a legitimate shift in between WGS 84 and NAD 83. It's very important to understand that most web mapping applications from, say, let's say AGOL, if you're using ArcGIS Online, it's natively using a WGS 84 coordinate system. The other thing to mention here is that satellites by default technically are using something called ITRF08, but that's actually like WGS 84, just a little bit different on a very long decimal number. My point here is if you are using a state plane coordinate system in Texas in a central system, that is a projected system. If we go back to Geodesy Drop, what you don't even see here is the last step. The last step is taking this globular object and actually transforming it into a flat surface, either through planar projections, conic projections, or cylindrical projections. And that's that last step. And when you make it flat, that changes everything. So if ArcGIS Online is using a global system, the World Geodetic System of 1984, and you're using a projected coordinate system, NAD 83 state plane, Texas zone 5 feet, there are differences there. The other thing is there's absolutely, if you look at the image on the right-hand side, we almost always never think about vertical coordinate systems in the GIS world. We traditionally have thought horizontally, like the X and Y on the map. But the reality is if you go into, say, Esri, you can go to your projection screen, your coordinate system screen, and at the top, you're going to see a tab And that tab is actually going to say vertical coordinate systems too. And so there are actual NGVD 29 based on stuff from 1929, and there's NAVD 88, which is newer, and technically NAVD 88, which you'll find in those GIS dropdowns, that is what we call orthometric height. So lots of things kind of intertwined here. Now let's really get crazy and blow our minds. So maybe you've heard of NatRef 2022, the National Reference Frame of 2022. Well, it's 2023. So if you're thinking 2022, what's happening? Prior to COVID, the US government came out and they are releasing a new coordinate system based on dynamic systems. And so NAD 83 technically takes into some account tectonic plate shift versus WGS 84. What NatRef 2022 will do, or what they call this, the NGS alpha, this NSRS, the modernized National Spatial Reference System, it literally takes into account live data. And so there are going to be changes temporally to how the data are actually sitting. This is mind-blowing, everybody. And literally, the National Geodetic Survey from NOAA, the National Oceanic Atmospheric Association, last week came out with the new alpha version of this new data. That's the other thing. We've talked about geodesy and we've talked about projections, but there's this whole other concept called datums, right? So how the data tie down. And in my mind, like, this is all like mind-blowing, right? Like, boom, like if you've ever watched Adult Swim, like we're talking about something super complex that literally is changing how we do data collection, right? And as being those professionals in field data collection, advanced GNSS and advanced data collection techniques, we need to at least sort of understand what's happening here. So I'm going to segue away from geodesy. I'm going to charge and challenge you that if that was enough to just go, holy crud, I had no idea what Nick was just talking about, go look it up. It's important. If you have not heard of NatRef 2022, this new system that obviously didn't come out in 2022, but I think they're calling it in 2025 or 2026. If you have not heard about this new system, perhaps you should look into it because as we all know, sometimes it takes a lot of work to get off of an old system. I actually deal with municipalities across the country that are still using NAD 27 as their datum, right? So most people NAD 83. NAD 27 doesn't even assume a center of the earth. NAD 27 is a system that comes from Kansas, and there was a ranch in Meade, Kansas, and literally from that location to the east and to the west, they built out the horizontal system. It's not as accurate as NAD 83, and you're talking about large municipalities that I've worked with that are still on a system that's 100 years old. So again, as we switch to this new system here soon, I'm going to say you probably want to start looking at this and how it's going to impact your daily business. Most major software companies and hardware companies are going to be ready for it. But are you going to be ready for it? Okay, so let's move on to kind of these advanced collection methods. You see here, I've got a bunch of different companies: Trimble, Geomax, Ike GPS, Leica, Garmin, EOS, Topcon, and I have Badolf on there. These are all companies that create GNSS or global navigation satellite systems. And again, I'm going to say that do your own due diligence, talk to the companies, talk to their local reps. Each company does something great. And over my 20+ year career in GIS, I've used all of them, and I can honestly say they are all really great. And we call this the democratization of data collection, or GNSS. You don't have to spend a fortune or give up your firstborn child anymore to go out and collect really great data. Okay, so let's talk about GNSS a little bit. So what is GPS? What is GNSS? What's multi-frequency? What's SBAS, WAS, RTK? So we're going to answer all of those questions here in just a minute. And all of those things are going to pipe down into what I would call consumer grade mapping versus mapping GIS grade versus what we call survey or engineering grade. So there are different levels of accuracy based on what you're trying to accomplish. So global navigation satellite systems, or GNSS, and you see greater than GPS. So in the United States, our system of positioning satellites is called global positioning systems. That is GPS. It's a misnomenclature to say that you're going to probably go use, like, I'm going to go GPS things. Well, nowadays, if we are actually using satellites from other countries, there's a larger archetypal term called GNSS. So you have a multi-constellation system. Most GPS systems these days have that. And so Not only are you listening to satellites from the US, you're listening to satellites from the European Union called Galileo, but also from the Russian Federation called GLONASS, and then also from the CCP from China, which is called BeiDou. And so lots of satellites out there. And so the more satellites you have, the easier this triangulation occurs. So the satellites shoot down radio signals. They have atomic clocks on board. An atomic clock keeps very precise time. We know the speed at which they travel. We know the speed at which the radio signal comes down. And so we can do some pretty cool math to determine the position on the ground. I mentioned 4 constellations from all over the world. The other thing is each of these satellites actually emit multiple signals. So these radio signals coming down from space, there's actually up to 3 or more radio signals per satellite, especially the newer systems coming online, like from BeiDou. So you may hear terms like L1, L2, L5. These are different bands of energy on the radio, basically on the spectrum of light, right? So the radio waves, these waves come down at different bands or wavelengths. And when that happens, we're able to use them actually kind of in concert to help add more data into the algorithm to provide your position. 10 years ago, to have quad constellation and multi-frequency would cost you upwards to $40,000. Now there are systems from around the world that are as cheap as just a few $1,000s. And even your cell phones, in some regard, are now adopting these types of technologies. It's important, again, to remember that all satellite systems broadcast their data in the datum WGS84, aka ITRF08. This is also the default Esri field maps collector setting. So if you're using field maps to go out and collect GPS data or GNSS data, know that your location profile is automatically set to default, which is going to be WS84. But that would need to be changed if you were going to use, say, higher accuracy systems like RTK, which we'll talk about here in just a second. You may hear about a term called SBAS. SBAS is called Satellite-Based Augmentation Systems. And in different parts of the world, we also call it WAAS, Wide Area Augmentation. So I mentioned these 4 constellations of satellites. Imagine that there's another set of satellites out there that just augment those, the first set. So all they do is basically like come in and assist to give a augmented result or observation. And so these other systems kind of float around and they help automatically. Back in the day, it was cool to just connect to them. Nowadays, it's like default, every GPS does it. And when you connect to it, this is something called DGPS or differential GPS. The other way you can have differential GPS, and when I'm saying in Art Collector, you would need to change your profile, is RTK, so real-time kinematic positioning. That's when you're receiving, either through a terrestrial radio signal or a terrestrial internet, kind of LTE, what we call N-trip, you would receive a correction and you can get down to survey grade. We're going to talk in a minute. These real-time correction networks are actually based on something called CORS, continually operating reference stations. So all throughout the world, there are permanently based GPS antennas on buildings and things. And usually governments might manage them, companies manage them, all different types of people. But these systems project and send out those real-time corrections. We have also things called VRS, virtual reference stations, where like a state like Texas, and TxDOT has an RTK network. You can create a fake CORS or an interpolated virtual CORS, which is called a reference station. Again, not going to get into the minutia of this, but suffice to say, if you see that word, you now know at least what we're talking about. And CORS is sort of like what we call base station. So if you've been around this game for a while, or you've seen a construction project, a lot of times you'll see, a land surveyor, GPS type person out in the field, and there'll be a tripod set up with a permanent antenna. And then you'll see somewhere off, walking away, another person with a GPS on a pole. And what's happening there is one GPS with a radio is broadcasting to the second GPS in a base and rover situation. It's exactly the same idea as a CORS station, except CORS uses the internet, where a base station is localized and it uses radio signals. So imagine that you are the person standing there, RTK rover in hand, and you got your little GPS or GNSS. And so you're listening to the satellites, radio signals coming in from space, right, from all those different constellations. Now, I mentioned the course station. This is that thing sitting on the mountaintop over here, right? This base or reference station. It's also listening to satellites. What happens is when you add in this extra correction piece, it broadcasts that via the internet, right? Mobile network to your data collector. And so your data collector can say go from a meter of accuracy down to sub-centimeter accuracy or centimeter accuracy, which we would call survey grade or engineering grade. And it really depends on what you're doing. If you just need to navigate around and follow the trail, you probably don't need RTK corrections. If you are doing riparian delineations for 404 permitting, if you're a NEPA person, 1 meter or better of accuracy is probably good enough to kind of show an ephemeral line of the water edge. If you are collecting utility data and you need to know exactly where that thing is, so you don't, accidentally put another pipe through it, that's where you might need to get into RTK. I also want to take a quick pause here, and I want to talk about this term I've come up with. I don't think you'll find it on the internet anywhere. It's just called TORM, TORM. Here's 4 takeaways you can walk away from today's sessions. This is why you're earning a PDH, right? So continuing education. What I would say is if you walk away with these 4 things, if you're ever outside data collecting, remember these things. 1, time. GPS do not all have, like all GPS signals or solutions are not created equally. If you are rushing data collection, you are in for a foul day because you can't rush math and you can't rush satellites and you can't rush the ionosphere and all these different things that are happening. So take a breather, take your time, let your connection happen, let your solution be good. Don't get to a point and just like tuck and roll and keep running with it. Like it's not advantageous. Like when you fire up that GPS, no matter the brand, the moment it gets a solution, it's got a solution, but that solution 2 minutes from now will actually be better than the initial solution. So give it time. The second thing is orientation. So what is the orientation of the GPS device or GNSS? A lot of them have antennas. And if you have a planar or a disc or choker ring antenna, like you see on the screen, those antennas are liking to be parallel to the ground and antenna facing towards the sky. Perhaps you have a helical antenna, like in a Bad Elf Flex, or even things like the Leica system, or maybe the Trimble Catalyst. These systems, well, not the Catalyst, but these systems have a different type of antenna that have a different orientation. So whatever your device is, understand that the antenna has a proper way to be orientated. Back in the day, Bad Elf used to have these little hockey puck units, right? And if you've been around Bad Elf, you've seen them. They're yellow and gray, and they're used all over the place. They look like Tamagotchis. The problem was everybody wore them on a lanyard around your neck. That lanyard, like if I have the lanyard here, right? The lanyard basically hung the GPS on the end of it. You looked like Flavor Flav and you had a clock radio around your neck. It looked cool, but the problem was it was 90 degrees off from the main orientation, so it was really degrading the GPS. Remember that. The other thing is resting or settling. And so if you're going to go up and collect a tree, or let's say you're going to go collect a water valve, right? Don't run up on it and just click the button. Remember, back to time. You want to let the GPS rest or settle. This is the concept of GPS inherently like to be stationary for high accuracy. Walk up to the place you want to collect the data, take a deep breath, take another deep breath, then click the collect button. What happens is the GPS settles and you will literally watch the RMSE, the root mean square error value. This is the computed value of like how good the accuracy is. You'll see that fluctuate based on just letting it sit there for a minute. Last but not least, I call it meat shield. It's kind of a funny term, but going back to the clock radio hanging from your neck example, your body creates a meat shield. So if you've got the GPS down by your belly button, which I've seen people do that all the time, like they're texting on their phone, what's happening is your body's actually causing half of the skyline to disappear. Radio signals don't bounce through bodies very well. They don't bounce through trees very well. They hate concrete. They hate metal. So don't let your body be an obstacle to good data collection. This is, in fact, why we have poles, we have backpack mounts, we have phone mounts. These things ensure orientation, and they ensure that oftentimes that thing is higher than your head. You ever wonder why there's 2-meter fixed survey poles? Well, it's to get the antenna above your head. So you walked away from today just remembering the concept of TORM when using GPS or GNSS. You have succeeded, and I can rest easily tonight. We've talked about consumer grade, mapping grade, survey grade. So this is a typical cul-de-sac in Phoenix where I used to live. You're wondering, like, he's in Texas, but he teaches at ASU. I taught in person up until COVID, and then my wife and I moved to Texas. She's finishing her PhD at Texas State, and so I'm completely online if you're wondering. But this is a cul-de-sac that if you've ever been in the Phoenix area or Scottsdale, Tempe, or whatever, you would they're all over. They're somebody in the design planning, like urban planning, somebody decided these were the way to go. And I like the representation because I can visualize what a cul-de-sac in a normal urban neighborhood looks like. And consumer grade is this sort of like 3 to 10 meters. Keep in mind your iOS phone or your Android phone will never qualify data better than 5 meters. You may look like you're getting better than 5 meters, and you might get better than 5 meters. You're using Uber and you're actually on the correct street corner. But what happens is the next day you turn on your cell phone and you're actually in the parking lot across the street, right? And so consumer grade, think about GPS on your phone. Mapping grade is the moment we want to get better than your phone and you want to have repeatability. This is called precision. This is where we're getting into 3 to 1 meter devices. And in fact, many data collection RFPs, requests for proposals today, require sub-meter, right? That's kind of where we're at. That's as you see last 2 weeks ago, seeing all the different GPS vendors there. That's the world we live in now. Why, to quote Charlie Trimble, accuracy is addictive. The moment you have accuracy, super duper accuracy, why would you not want that? Like, it's crazy, right? So 1 centimeter being a very discrete point in the middle. So recreational GPS, consumer GPS, maybe you're boating, right? And so you want to track where you're boating, or maybe you're hunting, or maybe you're fishing, or maybe you use all trails, or maybe you're a runner, or maybe like me, you have an Apple Watch and you have your Apple Watch follow you around when you're working out, which I do. These are consumer grade GPS, right? But the moment we want to actually start looking at utilities like a fire hydrant, right? Here is a survey grade GPS on a survey pole soldered to the front axle of a smart bike. So these are those bikes you pedal like half the time and then it moves you, right? And so this is a company called Engineering Mapping Solutions in the Phoenix area that literally skunk worked kind of a GPS tablet, Esri, and a GoPro camera, and they literally ride around doing conflation of utilities. Tell you what, in the fall in Cave Creek, Arizona, on an e-bike collecting GPS, that is like my dream job. I don't know about y'all, but I would ride around in Phoenix at 70-degree weather and go collect utility data all day. Those are the types of jobs you notice that the interns don't get sent out on, but the actual managers of the different groups do. That's a bad joke. But so advanced GNSS, we can keep going and going and going, but because I've only got about 20 minutes left or less, I want to roll on to the next subject, terrestrial remote sensing. Right. So remote sensing is the acquisition of information about an object or phenomenon without making physical contact with it. Think about your eyes. Your eyes are literally terrestrial remote sensing devices. A light or the sun sends down passive radiation. Light hits objects like me, my shirt, the wall behind me. When light hits that, it reflects off of the object, and your eyeballs are literally the remote sensing sensors. We suck in that data, your brain decodes the data, and then we utilize the data, right? And so literally think about your brain as a GIS, right? Every GIS has 4 parts. It's the collection of geospatial data, it's the storage of geospatial data, it's the analysis and the display. So your body using your eyeballs is collecting the geospatial data. Your brain is storing the geospatial data. Your brain and experiences are helping, whether nurture or nature, to analyze the data, and then you're displaying the data by your actual environmental actions, what you're doing. This is what we call behavioral geography. Exactly the same way a terrestrial kind of technical system works. Perhaps you've heard of True Pulse. True Pulse is a laser rangefinder. Maybe you're a golfer or you're a hunter and you've seen laser rangefinding. FYI, I'm a golfer and no rangefinder has ever helped me be a better golfer. It just irritates me more and more. But this is the idea that I'm standing back and I'm using a laser to shoot like a tree, right? And I can take that offset measurement. Why would you want to do that? Well, maybe there's a big road in the middle of it and you don't want to go, do the leapfrogger type of thing, frogger across the cars because it's dangerous, right? Or perhaps you want to collect the height of a utility pole or the top of the tree. This is the type of system that you can remotely capture that data. In a similar vein, there's something called LiDAR, light detection and ranging. It's not really new anymore. These systems have been around a long time, but also photogrammetry. And so really cool systems these days, just using your phone camera with a GPS and being able to stitch all those things together. So in Bad Elf land, on the left-hand side of your screen, you see a survey-grade GPS with a radio. So that's like a base and rover setup. And then in the middle, you see laser offsets. So you see an LTI rangefinder Bluetooth connected to your phone or tablet that then connects to the GPS so you can collect offsets. And then on the right-hand side, you see the same GPS being utilized to collect ground control points that we then use to literally set control and tie down the georeferenced imagery data, the ortho imagery from the drone. Quick shout out. This is Bad Elf stuff, right? All the other brands, for the most part, do this in some capacity. So I don't want to just get all lovey-dovey on Bad Elf. If you have a Trimble unit and you want to use a laser offset, don't be afraid. There's a good chance you're going to be able to do it, right? These are the new kind of standards. Also, ground penetrating radars are really cool remote terrestrial sensing technology. This is the idea that you send radar signals underground, they hit objects and they bounce back up. If you're a nerd like me, sort of think back to the original Jurassic Park, like OG Jurassic Park in the 90s. Dr. Grant, at the beginning, he's got this big old gun and he shoots it down into the earth and it comes back with an image of the velociraptor and then the helicopter lands, right? And in a similar vein, you send down a pulse of radar into the ground and it's able to find pipes and walls. And it's really used a lot for utilities. And it's also used for archaeology, finding underground burials. We've also can talk about things like this is Trimble's Spot. Leica's got one as well. Perhaps you've seen that show, Black Mirror. I think in the first season, they actually have an artificial intelligence episode where they have these robot dogs running around. Pretty frightening, quite frankly. But this robot dog can be programmed to walk on its own. It has a LiDAR sensor on the top of it. So it's light detection and ranging, creating full 3D spherical environments. And you don't have to even be anywhere near it. Or perhaps you've seen this. If you're a techie like me, augmented reality in a way is a remote sensing technology. We are interacting with the world from a remote stance. So Apple came out recently with what's called the Vision Pro. And so I'm just going to quickly show this while I'm talking, but this is the future, y'all. I don't know what else to say. Imagine this product is going to work just like your iPhone. It tracks your eye movements. You can pinch into the air. You can literally pull up imagery, GIS. You can, anything like you're doing in your iPhone, you can now put on your face. If you're a moviegoer like me, you can actually watch movies with it and make like a 500-inch screen on your eyeballs. This is the future, my friends. This is not like Geordi from Star Trek anymore. This is consumer. Now, a $3,000 Apple product is pretty expensive, but who out there buys a new Apple phone every few years for $1,000 bucks? Now, imagine the game changer of this. So, just going to keep rolling along. There's also systems out there. This is a Leica GPS attached to a system called VGIS, Virtual GIS. Virtual GIS is an augmented reality app that works with all your Esri data, your GIS, geospatial data. And it uses the camera on your tablet or phone to show you the image. And then it uses the GIS data to overlay it. And so you can actually real time make decisions. And if you're like a project manager, really, really help the process. And the picture on the bottom, that's actually augmented reality. So utilities lines being overlaid to show exactly where trenching needs to occur. And so these are the futures of kind of like this augmented reality remote sensing. Quickly, I want to take another tangential moment, and I did some research a number of years back on augmented reality with Dr. Phineas, Dr. Sam, and Dr. Iyer at ASU. And what we did is we used the total station to shoot in a gas line and an electric line. So we shot in with the total station to the most authoritative degree we could. Then we took an iPhone 8, an iPhone 10, a Bad Elf 1 meter unit, and then a Trimble R2, which is a fully survey grade unit. And what we did is we basically used these with a custom app to collect the data of those paint markings, those lines we shot in with the total station. So what you can see here is on the left-hand side, this is the iPhone 8. And so the dashed black line is the total station utility. The red lines is your phone trying to do augmented reality to recapture that line. On the bottom, it's doing the same thing, except it's doing it with the other utility, right? The moment you attach it to a GPS unit that say has a 1 meter accuracy, say from your cell phone, you can immediately see on the top here that the red lines much closer meet that dash line. And then for the yellow one, they're almost spot on. You notice that even with a 1 meter device, you have some outliers statistically. The bottom right here is a Trimble R2 with an RTK network involved. And so we were collecting centimeter level augmented reality data, and you can see that it fell really close. There's a bunch of math just to show you that I'm not making these things up and it's not anecdotal. This was actually tested. And so the point here is that augmented reality is here. We can do some really cool, it's not even really cool things. It's like, it's actually here. And if you attach an augmented reality device to a high accuracy GPS or GNSS, you are actually able to do real-time awesome work. VGIS is amazing. They're out of Toronto, Canada. Highly recommend you take a look at them. Obviously, there's other options out there as well. So 2 more pieces. Earth observation. So we're getting away from the Earth and we're going up into space. So Earth observation is the gathering of information about the physical, chemical, and biological systems of the planet. It's done via remote sensing. So I want to talk really quickly about satellites, right? If you've been around recently, you know that there are all kinds of satellite options out there. And honestly, the one I want to kind of target today is the CubeSat. So the small sat, the ones that are, you see there that say by Planet Labs, Black Sky, Terrabella, or Blackbridge. These are satellites that are smaller than you. And in fact, you can put a satellite in space with a camera on it for about $50,000. Well, of course, that $50,000 small satellite's not going to do a digital globe world view 4 does, right? There's no way there's an order of magnitude difference there. But the cool thing is it's what's called repeat pass. So these big satellites, you have to task them. That's the process of asking the satellite to go do your job. Well, you have to get into a queue, you have to pay for them, etc. Small sats have the ability to do complete repeat passes, and you can kind of micromanage them. So if you wanted to see vegetation management over the course of every day or multiple times a day, it'd be much more affordable to use, say, like a small sat to do that. So lots of really cool satellites out there. And in fact, if you go to Wikipedia and you just type in Earth observation active satellites, I just took a screenshot here from A to C, but this list is like 5 pages long. There are a ton of satellites out there that you can access for data. 20 years ago, I remember during interview processes for GIS jobs, they would literally, you would be asked, like, can you find the data? And I remember on one job interview, I had to explain how I'd go to this discrete BLM field office website and talk to the person to download a cruddy shapefile, et cetera. It was awful. Well, today, that's not the case. There's data everywhere. 2 other remote observational technologies I quickly want to touch on is synthetic aperture radar and interferometric synthetic aperture radar. So synthetic aperture radar, you've probably heard of, or maybe not, but it's called SAR. SAR is the idea that we're sending now a radio signal just like GPR, but from a satellite to hit the ground, and you're able to detect differences in elevation and such. INSAR works in a similar way, but what happens is it takes 2 passes of 2 satellites and you measure the difference in between them. So if you're measuring subsidence and uplift or changes due to large industry, or you're studying the Permian Basin or agriculture impacts, things like this, SAR, INSAR, check them out. These are not crazy technologies anymore. You can access them really easily. One of the coolest examples of SAR usage is measuring the weight of ships. So imagine that you have a harbor and you are able to use SAR to determine the water level. And then as ships come into the harbor, you can use SAR to determine where the water level has changed to, because the ships are displacing in that local area change. To me, that is super neat, right? I mentioned data, and I'm wrapping it up here. I'm going as fast as I possibly can. If you want to get SAR data or INSAR data, check out the Alaskan Satellite Facility, ASF. If you're a government agency out there and you have to do any type of erosion, subsidence, anything having to do with the earth changing the ground, check out Alaska Satellite Facility. They have a ton of data sets that you can find, you can use. They've got plugins, etc. The other thing is, I'm going to plug Esri. The ArcGIS Living Atlas is awesome. I was at the Texas GIO meeting last week, and I heard from NOAA that they're working with the state to produce this new coastal mapping stuff, right? And this new imagery stuff. And I mean, it's going to be available at some point on the Living Atlas. So if you've never used Living Atlas on ArcGIS Online, highly recommend it, whether you're using Sentinel or whatever. There's a ton of amazing data sets that are constantly being updated from all the major federal agencies out there. I've mentioned TERRESTRIAL a few times. TERRESTRIAL has an awesome data portal hub that you can go on and find a ton of really cool stuff. They have a ton of old imagery if you want to go back temporally speaking. Lots of really great stuff there. By the way, did you know Google Earth has temporal mapping as well? So if you want to say pull up Google Earth and you can pull up the time bar, and you can go back in imagery, and you can actually see like a temporal analysis just by cycling through. So future of GIS. And I'm using Smart Brevity format, plugged to the book Smart Brevity and the writing style. If you've never checked that out, ever heard of it, it's from the creators of Axios and Politico. But unleashing spatial intelligence, mapping tomorrow's world with GIS. I wrote this for this presentation. I wrote, the future of GIS involves enhanced real-time data integration, AI-driven automation, expanded Internet of Things integration, and increased application for urban planning, disaster management, environmental sustainability. So really all of that is driving towards what we call the digital twin. This is another buzzword, but it's huge. I just read that the geospatial market between now and 2030 is massive. Check out the marketing company Geospatial World if you want to do some financial trends. But all of this is pushing into the digital twin. Wikipedia says a digital twin is the representation of an intended or actual real world physical product, system, or process. In today's terms, a lot of times when you build buildings, you've heard of BIM, building information modeling, that is a digital twin. Utilities, digital twin. It all originates from NASA, actually, right? So if you're designing a spaceship, you need to know where every nut and bolt is. And when you're looking at these different pieces of the design, whether it's a smart city or a turbine engine, the idea is the digital twin is not just spatial. It's not just 2D. It's not just plans and maps. It's not just 3D, right? Visualization and orientation, but it's 4D, 5D, 6D. So if you ever hear about the 6Ds of digital twins or BIM, 4D is the time, 5D is the cost, and 6D is the project lifecycle. So if we had the 6Ds of every object mapped on Earth, imagine the power we would have to make informed decisions. So in the world of subsurface utility engineering, or SU, this is a major thing today. So this is a surface cut in New York City. That's what it looks like underground, right? And so you think we probably should map those things? I would say so. Here is an example of actually a pipe strike. So contractors didn't know where a pipe was. They hit a gas pipe and they blew up a building and people died. So if we don't know where we are, we can't make good decisions and people will lose their lives because of it. This is a little bit of a disturbing video, and we're only gonna have about 5 minutes for questions. Promise nobody dies here. But the idea is this person doesn't know where their things were, and that post hole digger hit a pipe. This is problematic, right? And this is where like the future of GIS is really knowing where everything is on the Earth for better decision making. And SU, subsurface utility engineering, a standard by the American Society of Civil Engineers 38-2, actually requires you, as you start putting in new utilities, that you have to map them at a certain degree of accuracy. I'm not going to go into it. Remember that there is accuracy and precision. Accuracy is how accurate you are to a known location on the Earth, whereas precision is the concept of how accurate you are to your own data set, right? So it's the repeatability of collecting the data versus how it falls onto the Earth. Both of these things are important. What you really want is this top right-hand corner, precise and accurate. If I could shoot like that, my long rifle, target shooting with my wife, that'd be amazing, but I'm usually not even on the board. But that is what we're looking for, right? And XYZ marks the spot. So if we collect cruddy geospatial data and we don't know the geodesy and how it's created, basically crud in, crud out, right? So you have to start with a good position or POB. That's the point of beginning. And I joke, but the digital twin begs you. And the future of GIS is built on this concept of the digital twin, artificial intelligence, collaborative web GIS, autonomous vehicles, real-time big data, chat GPT, GeoInt, and the list goes on and on and on and on. These are things GIS is now being utilized for, but it's all wrapped around knowing basically where everything is, right? Ezra used to say the science of where, or seeing things others can't, or creating the world, creating a better world with the use of GIS, right? If you have been following me and you were at a SCOG conference recently, I did a keynote speech and I gave a couple quotes out. I am stealing that quote again because I like it so much. I'm going to challenge y'all and charge y'all with, in the future, artificial intelligence won't take your geospatial job. However, someone using it will. So if you go back here and you've never heard of ChatGPT, go Google search that today. If you've never heard of AI, machine learning, things like this, go Google search that today. You really should start considering using it on the day-to-day, because perhaps if you're not, your job could be gone. The other thing I would say is, I call this the geospatial moment. This is the time we're in right now. Our geospatial moment is here. Don't blink, you might miss it. There's never been so much LBS, location-based services. There's never been, I mean, John Hopkins and COVID and that dashboard changed the world. Everybody used that map, right? So we need to take charge and really push this moment forward. And that really does start with collecting good data in the field, because you can't really do analysis without good data, whether it's collected from a satellite, a drone, a LiDAR sensor, or a GPS. So I am going to end with this. The future of GIS is you. It's me. It's us, right? It's we. It's not them. I really want to kind of be equitable and inclusive here and say that we are the future. So it is up to us to make sure that this geospatial moment is profound. It is up to us to make sure that in 20 years, Skynet doesn't come self-aware and we're all killed by AI. It's up to us to make good decisions with the mapping. COVID showed us that you can lie with maps. You can lie with statistics, right? Mon Monkeyar, check out that book, How to Lie with Maps. And so it's up to us to be the future. So I have 5 minutes left. That is, I will answer as many questions as I possibly can. Thank you again for Urissa, for all of this.
All right.
Yeah.
Great, Nick. Thank you. So we have a couple questions here, and like you said, we have 5 minutes here. So Carl Coleman asks, my question revolves around the idea of indoor mapping, specifically tracking firefighters inside a multi-story structure that is on fire. How far out do you think we are to being able to map accurately indoors?
Great question. So there is a conference, a trade show once a year called Geo Week in Denver in February. They do a lot of indoor mapping there, but we're pretty close. So in the Esri world, there's something called ArcGIS Indoors that incorporates that. But in a lot of these buildings, you can have Wi-Fi connect. You have Wi-Fi routers. These Wi-Fi routers can effectively be used as positioning devices. And so I actually think, as we march towards the digital twin, as new buildings come online with that digital twin built, you have an outline of the entire building. You know where you are, like you have that structure. And so then you just have to place yourself within it. And there's some really, really neat technologies coming out for indoor mapping. And so maybe not next year, but I would say within the next 3 to 5 years, you're gonna see this be pretty pervasive, especially with augmented reality. Because what I didn't show you was, they have augmented reality helmets, like you put on your construction helmet or your fireman's helmet, and there's a Google or a Microsoft HoloLens attached to it. And so imagine having the ability of augmented reality to see a heads-up display of the building as you're running into it to stop fires.
Super. Thanks, Nick. So we have a couple more questions here. So Amy Dunn asks, one factor keeping us from data collection in the field beyond basic GNSS locations is the effect of heat on technology. What are the best tablets or other hardware that have decent battery life in the heat of the Southwest? I've heard good things about iPads with Esri apps, but one of the cons users mention is that they don't do well in the heat, sun, or glare.
Great question. Yeah, especially with the extreme heat that we're going through right now, every hardware is having problems. And so there are ruggedized tablets and phones out there. You just type in ruggedized Android tablet and you're going to find a ton. And what they do is they create them in such a way that if they get dropped, they're not going to bust right away. They have a little bit of higher heat thresholds. The other thing, say for like iPads, is the type of case you have on it. Make sure that there's airflow going into the case. I also recommend in between data collection sessions, bringing it into the car using AC. I've literally seen ice packs attached to it, kind of with wraps, keeping it out of the shade. So best management practices. Unfortunately, there's not a lot we can do. I mean, and iPads, I will be honest with you, a normal iPad in 110-degree weather is not going to last very long. And so finding that ruggedized option, and again, you can reach out to me afterwards and I can plug a couple different versions, but yeah, you're going to want that. And then keeping aware of the environment. So I know it sucks to get up at 4 o'clock in the morning to go survey when the sun hits you in the morning, but that's like, you know, a land surveyor would be out at site ready to collect data the moment the sun peeks through, where sometimes us GIS people were like, I'm going to go to the office, I'm going to drink coffee, and around 10:30, 11, I'm going to leave the office and I'm going to grab lunch. And at 1 o'clock, I'm going to go collect 100 points. And we all know we do it. So I would recommend best management practice. Fun fact, there are USB plugins with fans. So if you have like a tablet with a full battery or you have an external battery, you can actually plug in little fans. Where I've seen those being used in the past as well.
Cool, cool. All right, so there's actually a handful of more questions in here, and we are unfortunately running short on time. I will kind of toss two questions into one. How are you using AI? What are some resources for AI and GIS that you are aware of? Absolutely.
Am I using AI? Yes, I am. I use AI regularly, particularly ChatGPT and Bard. And I use them for more on like communications, emails, writing, thoughts, decision matrices, using them for Python code, stuff such like that. I don't do a lot of analysis these days with machine learning or augmented reality, but like random forest is a really cool thing right in ArcGIS. My biggest thing is, well, I'm going to plug another podcaster. His name is Lex Fridman. He's a PhD at Drexel University, has a very famous podcast. He has like AI people on there all the time, like Sam Altman, the CEO of OpenAI from ChatGPT, things like that. And they have a bunch of really good resources out there. My suggestion is just jump in, start messing with it. Just be careful. Yeah, just be careful.
All right. Well, folks, that's all of our time for today. It's 1 o'clock. We'll go ahead and end the meeting here. Thank you all for attending. And Nick, thank you so much for the wonderful presentation.
You guys are most welcome. Thanks, everybody, and stay cool out there. Remember, you know, safety is no accident, so drink up water. Stay hydrated.